So Wenzong said goodbye. He had to go.
Oh, he's gone.
Yeah. Just not too long ago, about 20 minutes ago. So I think he stayed for most of that. I'm not sure.
Yeah, he said that he will be going.
Yeah. I know, it was great to see him again. And his work is based around the Hubble constant as well, isn't it? So I'm sure he was probably be sad to hear that the Hubble constant is not actually a constant. I wonder if that would affect his work. Interesting to see, like, would it affect his work?
Yeah. Possibly. So I just show you briefly. This is the one that is now published yesterday. I think that it went on publication yesterday. But the DOI has to be activated. But this you can get it the internet. So this is physics formalism. This is the paper that is before our paper. It's our paper quotes this paper, but it's under publication. In our in the Helmholtz-Gage paper, the PDP Circuit paper, it quotes this paper because it's based on this paper. It bases a lot of things on this paper. But this so it's finally published
afterwards.
Yeah.
Okay.
Yeah. So this is the one. So it shows how the gauging is done. It shows, from the previous one, from the Iyer Markowitz thing. That's the first one. So it's a continuation of that. The continuation takes on, and that continues. I think I give this presentation. In the presentation also I gave this.
Rajan, could you increase the size of the document?
Oh yeah.
No. I click the plus button. Oh yeah, you can do it that way as well. Cool. Great.
Is it okay now?
Oh yeah, it's brilliant. So does this also have the eigen vectors or something, or the eigenvalues?
Yeah, it has that the Helmholtz decomposition. This is the rotational or vortex field.
Yeah.
And because the Helmholtz decomposition says that any point, any field, there are two. It can be split into two fields. One is the vortex or the rotational field. The other one is irrotational or gradient field. The two types of fields. Yeah. That's a fundamental Helmholtz decomposition theorem.
Okay.
So that's what I'm using. So it can become a gradient field, or it can form.
Did he freeze for you as well, Corrado?
The gradient field.
Did he freeze?
That's it.
You froze just for maybe 10 seconds.
Okay. Can I continue now?
Yeah.
Okay. So this is the main idea, and the rotational field can be up or down. So it can, so we have the tensor. This one is rotation field down, rotation field up. This is gradient field down, gradient field up. So using these, we can build everything else. That's what I'm doing. So we can convert this field into gauge it, and then and the previous one with the Iyer Markowitz thing, I have shown that we can, we can derive a partial differential equation that shows connection between the field and energy and all that. So that's a long equation, the time evolution and everything. Okay.
Yeah.
But I'm not going to go into detail because it's just derivations that paper has. So we can gauge it to a Coulomb gauge. So Coulomb gauge, which talks about the electromagnetic things, and also Higgs field, which talks about the mass, the matter, the mass of the matter. And the Coulomb gauge is electromagnetic, whereas the Higgs matrix is the mass that shows the matrix. So I can gauge it, and I can say this rotational field is connected with the mass matrix, the Higgs type mass matrix, and the G's are the Coulomb gauge, which is electromagnetic. So when I put that into equation for the vacuum, we see that the vacuum gravitation, you have this G and minus G, but here this will become 0, but there is a mass remaining, and we mentioned that this shows that the vacuum, it's not empty, right? And you mentioned that you also find very similar things, Christopher. Yeah. So using the determinant, I can convert this, and I can say this is negative G to the inverse. Yeah. And so there's an inverse relationship here, and also negative G, and I can calculate the I value, the determinant of that, which is negative I, which is the value, the magnitude of -1. Okay, magnitude of -1. So because of that, I can extend this. I can extend this to infinity almost. So this G and minus G will talk about, I can connect with the Coulomb gauge to positron and electron, whereas this one is connected with the mass.
When you're saying you can expand it, is that because it's a generator? Is it just rotating?
Yeah, it's a generator, because the minus G I can substitute again. You see that? I can substitute this value over and over. Because this is minus G, I can minus is because of this of the determinant. I can make the determinant go to 1. Then I have to extend this as a matrix. You see that minus G, I can reevaluate the matrix. Okay. Yeah, so I just reevaluate the matrix. I get this, the matrix over and over again. So the minus sign, because this value of this is -1. You see that? The value of this matrix is -1. So I replace the -1 by this matrix.
But it's not just, you're not just repeating the matrix, because it's the matrix times the other matrix, and it's has. Yeah, it's interesting. It's funny, isn't it?
Yeah. Yeah. But you can, when you do that, you can actually get, because this is this negative value is a matrix, the value of a matrix, So it constitutes a matrix. It's not just -1, it's negative I, which is a matrix value.
Yeah.
So I have to replace by matrix. It's not just a number. So the whole thing, the value of the whole thing is -1 or negative I. And this value here is actually a matrix value. So I have to replace it by a matrix. So that's what I am putting here. The -1 I am putting.
I think I understand. Like, I don't understand everything, but I understand that.
Yeah. So that's how I can extend each one. I keep expanding. I'll still get negative here. So I have to put again like that, It's like a string, it keeps going.
Cool.
So that makes sense. Yeah.
And what is the physical result of that? Or
the physical result is that this G minus G is electron and positron. And so this electron positron, it's string of electrons and positrons going along this direction.
Oh, that's cool, isn't it?
Yeah.
That's
and then you have the mass of the particle. So these are like quasi-particle almost, electrons and positrons. But here the mass, here it extends perpendicular to that, but it's not exactly orthogonal, which means it is asymmetric, and that combines with John's work and other things that and also it says why. Maybe it will answer the question. I mean, we have to rethink about it, about the left electron, the right left neutrino, and the left neutrino may make sense from this one, because it's not really symmetric, the symmetric matrix.
Yeah.
So they don't cancel each other. Yeah, they don't cancel. Okay. So that's the big, yeah. So I think this can be used for a lot of things later on, but this is fundamental.
Let me ask a question. This is a question that kind of based on one that John brought up a while back. Like he was, so let's say, or let me frame it a different way. Like if you, by the sense of it, seeing as how you're trying to build this circuit, yeah?
Yeah.
Like you'd want to kind of manufacture the circuit, correct?
Uh-huh.
So, but how many of them do you need?
Okay, we start with the, okay, the simplest one is just one circuit to start with, and look at the rotations that we have put the scenario for that, right? The number 10, I think, figure number 10 in our paper.
Oh yeah.
It's a scenario. Yeah.
No, but I'm talking about like in reality, like
in reality, there'll be a lot of them like that. So like functors, they will act like functors.
Okay, so this is related to the question that John was asking then, because like one of the components within the PDP circuit is a positron, and positrons are antimatter, and antimatter is not easy to come by. So if you need one positron antimatter particle in each of the circuits, and you need a lot of circuits, then you're going to need a lot of this dark matter. And how are you going to get it? One, how are you going to contain it? How are you going to work with it? Have you thought about this, or is that sort of?
Yeah, actually, that's what our computation will see. That's why we start with one and see how many we can put actually. So there may be a limitation, automatic limitation based on what is possible with antimatter. Automatically the limitation will come there.
Okay, I understand. So this is very theoretical. Like
very theoretical, yes.
Yeah. So like in an ideal universe where you could generate a lot of antimatter and contain it.
Exactly.
This is a potential thing. Okay. That's cool. Okay, go.
Okay. So that's the main thing. So this is one of the main things that comes out of that. Then we have the proof formalism. And actually, I got another letter from one of the London journal or something. They invited me, their invitation. They said that the proof formalism I did with the Malaver, remember, that's a fundamental thing. I'll talk about later probably. Or I don't know. Yeah, I don't want to confuse it now. But the proof formalism is a fundamental derivation of the based on the matrix properties. So you can compute a functional. Remember functional. Functional connects between two functors. So the functional, this is the quantum density matrix that we are.
Oh, you froze again. Or maybe you didn't. Did you freeze?
We talked about last time.
Okay.
This could be connected to, this could be connected to a even as a bottom quark and top quark. I think you can do that, the wave function. So that's, but in our PDP circuitry is the bottom one and the top one is revolving. So that is a wave function, the wave functions of that. And then you need the inner product and all of those things, inverse of that. I use this later on in our next paper. I'll show you later. So then a scalar potential, then you have this, this factor, which is again scalar potential times the, why is the V coming? Let me check. Oh, I didn't check that. Okay. So it's an additional factor that's coming in. So V is del mu V. Yeah. So this is G. Okay, there is a comma here. So I think.
Is it velocity?
That's why it's, no. It's actually a scalar potential. But I think, I didn't look at that. I already told them. I don't know whether they can change it, but I think there's something missing here. Anyway, there's a space or something. There's a
gauging V equals what is the modulo of the delta E.
Yeah. So this is the correct equation. Equation 10 is correct. Here some correction has to be made, but it's okay, I think. But the equation 10 is okay. So I just change it, and so you have the wave functions, then you have the scalar potential and the quantum density matrix. That's it. So they are the fundamental things. And now I can, I can say all these are equal to some function, because this is a function inside the functor, you know, our like PDP circuitry, it acts like a clock. So it's a function. So you have the wave function and the scalar potential, they all work together. So they form a nice function. And then the G, which is the coupling constant with the quantum density. So we get the matrix G, which is the Coulomb matrix, the Coulomb gauge, the Coulomb gauge G. So, you know, this is all fundamental, you know, just a derivation math, but it's straightforward. It's a substitution. So that is, so from there, I can say, you know, you can make, that's why we use it, you know, and these are all there, I said, where we can use it. Like you can find the extended matrix for Coulomb gauge. I talk about, I think, the on-off circuit, which is we can say which one is on, which is off, things like that. It may touch upon your work later on, but I'm just giving an example. I didn't go into detail here. What are the applications? And then we can do even Feynman diagram using electron-positron generator. That's what I was talking about, electron. And then we use this monopole electron-positron in our PDP circuitry. This essentially we're applying to PDP circuitry in our paper. It comes after this paper. Okay, so this is where I talk about the electron and positron that I already talked about. So essentially, it is, yeah, it's essentially, you know, it's a prior thing to our paper, but it sets the stage, you know, and then so that's the main thing. Then let me go into our gauge. You can see. So this is a gauge discontinuum, and I'm working on. I started. So it's called Gage Discontinuum Space-Time Observable Quantum Circuitry Astrophysics. So I'm interested in the observables, you know.
Rajan, can I stop you there? Sorry to interrupt. Yeah. One thing that you're not sharing, if you've switched to a different document, you're not sharing that document. I can't see it.
Oh, you cannot see this?
No,
let me check.
You need to switch your, you need to change what you're sharing. It happens to me all the time. I could see your mouse moving across the screen, and I was like, yeah, I can't see that.
Okay. Sorry. Let me.
Hello. Very interesting.
So let me see. Why is not?
What are you reading it off? A browser or?
I have two browsers. Let me check.
You'll have to switch to the other browser then.
Are you able to see anything now? No?
No, just the same screen.
Same screen. Oh, so okay. So let me. Yeah, okay. So I will just stop presenting and then re-present, I think. So I think.
Good idea.
Can you see now?
Yeah.
Okay.
Can you also embiggen that? So,
yeah. Let me increase the size.
A much better way of saying it. Yeah. Okay, so engineering international. Is this the one with the 6 authors? Oh, great.
Yeah.
I'm in there. Manuel, John.
Yeah. So a whole lot of people. Wen Sang.
Why did you put it Wen Sang with an @ sign? That's his address. Is that
I had to put the correct thing here, and he has to put exactly because he puts different thing, different places. So that's why this is to, so he can put the correct way he wants it there, and then he says, so everybody has to put their affiliation. Like 1, I will put my affiliation as 1. What the affiliation? affiliation is your affiliation 3. I think your affiliation now with CCT college probably. I don't know.
Yeah.
So you have to put you can put your, like I'll put 1. Eventually this is just an initial thing. Once we have our paper in a draft form, then we can start putting our affiliation, and you can change all these things. We'll just clean up all these things. But and then 3, the John Hodge, again you have one is affiliation. When Sang its proper name, and also affiliation. Emery Taylor is the other person I'm working with now. It's about discontinuum theory. He has a paper written about falsification of.
Sorry, go on
Go
there.
ahead.
Oh, right. Okay. I haven't looked into Emery Taylor. Is he on ResearchGate?
He's not on ResearchGate, but he's from Massachusetts in the US, and he has moved to Indiana. He has attended a lot of the original relativistic talks with people. I think even John Wheeler and all those people, and he was in their group. So he has a lot of experience. So he sent me a lot of paper about Newton's Sholem original papers. He has original papers on Newton, very original. A lot of paper. I couldn't go through all of them, but Newton is extensive work. It's called Sholem, Scholem or something. That's where he discusses all that and come up with these all these theories. So it is a very very detailed thing, very powerful.
Do you want to? Yeah, I haven't heard of this Shalom. You want to? I'm just going to admit your phone or whatever needs to. There we go. Okay, so what is Shalom? Is that Newton? Hello?
Are you able to hear me?
Yeah, I'm wondering maybe.
Sholem is like.
Go ahead.
Sholem is like a proposition, or it's not a hypothesis. It's like concept, I think. Sholem is more like concepts.
Never heard of that before.
Yeah. Scholem or something. But that's old English. Maybe it's old English, because Shakespeare English, even before, he is in the 16th, 17th century, right? Newton. So it's old English, archaic English,
Yeah.
Yeah. So that's why, but it somehow made sense to me. I heard it somewhere else, but it's archaic, I think. I don't know whether it's there in the dictionary anymore. I didn't check it. But in any case, so he goes through extensive way of, how we come up with this F equal to MA and all those things, It's a very detailed thing. And he has a lot of geometry. He considers a lot of geometry, analytical geometry, algebraic geometry, from which he comes up with these equations of motion, F equal to MA, and all other inertia. How we come up with the first law. It talks about inertia, and especially about light. Why the light continue to move, the motion of the light. Why it continues to. He has shown some geometry which shows that why the light will continue to move. So that's the first law. Anything that continues to move will continue to move at a constant speed. Uniform motion, law of uniform motion. So all this he derives from geometry. It's a very detailed thing. But what this person has written is something about. I think I may be able to share that. Let me see. I think he has. I'll stop sharing these and I can share the other one. I'll show briefly his paper. I think I should be able to pull up. Let me see. So, No, I can. Oh, from this I cannot project. But at some point, yeah, I'll show later. But let me continue with this one.
Yeah, great. So have you written much on this paper?
Not a whole lot, but I started the idea. The idea is that, so I came up with the idea that each person does 2 pages. So you will have 6 sections, 12 pages of the. So I will start with the first section. I started a little bit. So I complete the section, then I will send to all of you, and you can add your 2 pages that connects with all that, your side of it. And then we have then 12 pages of draft, right? That's our initial draft we work with. Then we start working on that and making it a meaningful, thing, continuous thing. But then we have enough material to work with, And then after that, 12 pages, once we finish that, we can send it to Alexi, Canadian Journal Pure. I don't know whether Alexi should be there. Maybe his work is not related, but otherwise he can also be included there. I'm not sure at this point.
Yeah.
Okay. Yeah, so here sure. I'm talking. Yeah. Okay. I start with our PDP circuitry that we talk about that scenario, many scenarios in our thing, right? Then the figure 10 is the best scenario, finite element modeling, for computer programming that you're going to do. So that's what I'm talking. I had to redo these things, because if you are doing a separate paper, I might remove some of it and we will have a different paper. But the main thing I am trying to emphasize is about observable, observable physics. So that's where the figure 10 comes into picture. But the Helmholtz, your north-south monopoles attractive, right? They were unlike poles, so they're attractive. Electric tensors are parallel, hence repulsive. So I'm just going through our figure 10 in our paper. So the electric tensors are parallel, hence repulsive. So they are two, the two fields. So electric tensors are there, but they are all pointing the same direction, so they'll be repulsive. And each particle exerts force on each other. So we have a lot of forces going on. Electric forces, tensors, magnetic fields, they are exerting their forces. So the symmetry rule, I have done it separately. The action of attractive is balancing the repulsive to keep apart. So the idea is that why they don't collapse immediately? Why don't, if you have electron positron, you will say they will annihilate automatically, right?
Right.
But they don't annihilate because there is also the magnetic things going on. So the magnetic things will not allow them to will not allow them. They will keep them apart. The magnetic field, because they'll keep them apart. They won't allow them to approach to each other. That's the idea. They won't they will approach to certain distance, but they cannot go beyond that. So we'll keep the magnetic field will keep them at certain separation.
Wait a second.
So they will
I have a question. I think I already asked this before, but what about the Heisenberg uncertainty theory, which says, like, let's say you have one of the particles here and one of them here, but because of the uncertainty principle, it could be over here. And then if it's over there, then it annihilates. Is that an issue?
Yeah, but the thing is that you remember the size of the PDP circuitry is 10 to the power minus 26. Whereas the uncertainty principle, the Planck distance is 10 to the power minus 34.
Okay, so you're saying space that it won't happen.
Yeah, so it may be, 10 to the power minus 26 is here, right? 10 to the power minus 34 is here. So again, there is still, what we call, so you are this distance, but this distance is uncertain. But still, if it is like 1 centimeter versus 1 millimeter, right? So you have it could be 1.1 millimeter difference or 0.9 millimeter, but there is still difference. Even if you take into account what I'm saying, you understand what I'm saying? Does it make sense?
I don't know. I think I understand. Like I don't. What you're saying is that there's enough room for this.
Yeah.
This is so you've taken this into account.
Oh yeah. So even if we take into account uncertain principles, still there is enough, enough distance that they will keep separate. Even if the uncertainty principle makes it difficult to gauge exact distance.
Yeah.
Yeah. I think physically they'll be enough. They'll be separated because of the magnetic force. The magnetic force will not allow them to, because they also had to. They will start to attract each other. So the magnetic force also want to come together, but this one is perpendicular. It will not allow. It will then it will interfere with their thing. So all of them together, they'll try to keep a distance. And they'll start rotating. When they keep distance, the only thing they can do is rotate, to keep the symmetry. Yeah. So I think we should be able to prove that eventually. I think there is a way that anything that keeps a distance will start rotating. I think there is a transformation that automatically shows that. I think we should be able to prove that. Now I'm going to remove some of it. I'll just add it. Okay, I'm just going to discuss partly this picture. Then I'm going to briefly only. I don't know. I will include all of the picture, but it's just a picture that talks about entanglement versus mixed states. So I thought it was interesting. I had to rethink about that. But entanglement means it could be a natural or it could be pure. Okay, which means mixed states. So natural state, in the sense that natural state is where they are in the decoherent state. They are separate, like monopoles. The monopoles, for example, they exist in their own forms. Where pure state is, they exist as dipoles. The pure state, they exist as dipoles. They can exist only as dipoles. In the same way, electrons and positrons, the pure state, they can exist as the natural state, they exist as quasi-particles. Whereas the pure state, it could be the other way around. I have to really think, but I think the pure state is where that when they talk about pure state is where they exist like what we see as neutron, as a neutrino or something. When they combine and they form neutrino or something, they exist as a particle. So in the pure state, they exist as particles. In the natural state, they can exist as quasi-particles. So that's the idea here. I have to rewrite these things. This was some time ago I wrote that. Then I talk about statistics and all, how to do statistics. I think we will do separately that aspect. Okay, just from the literature, right-hand rule, left-hand rule, to ensure that we follow these magnetic field, directional magnetic field. That's all. Okay. So these are all normal things in the Wikipedia. I'm just putting it to ensure that we follow those rules. Yeah. Then I have this one. Yeah, this is the one I'm talking about, the wave function, So my conjecture is that this wave function times this wave function times this Coulomb gauge. When you solve for gravity, and I'll show separately. When you force gravity, it becomes equal to the cosmological constant, which Hausen field actually shows that this cosmological constant gives the vacuum energy density, which is constant. The vacuum energy density is a constant, actually, universal constant.
Okay.
So the sigma, the psi subscript u mu and psi subscript superscript mu, they are the wave function. And what I'm saying is that eventually it can connect to John's Horde, principle, the up and down structure, which then connects to quark, for example. He said that one quark has so many hordes, right? When you put them together, you can form a quark. He has a theory that shows that quarks. So if you have a down horde, up horde, that's at almost the point level. Then they can form like an entanglement and form different things, quarks or photons and everything. I think if we can use this to show that will be great. And then here, these are all functions of time, but this time is a gauge time. So it's a vacuum gauge time. And I think that it can be connected to we are going to connect with the discontinuum theory. We are working on it now. We'll be eventually working on it. And I have some write-up on this one, some fundamental proof I can show you. Gauge proof. I think it's a very fundamental thing. We can use that mathematical proof.
That's great.
And then this, yeah.
That's great. I was going to say, well done on the, hang on a sec. Yeah, I was going to say, well done on bringing John's work into it. I really like that.
I thought it's very important because he has, it's a very fundamental thing he's talking about. So I thought it's quite important to bring him in.
Yeah, for sure. I agree.
Yeah. And then this one is Emery that I'm doing the math on this one, but the Emery is doing the discontinuity theory, falsification of relative. Emery is talking about falsification of Einstein's theory of relativity. It's a big thing. He has written a thing why Einstein's theory of relativity may not be correct, things like that. But I'm going to dilute it. I don't go to that level, but I think he'll be okay with him. But I will de-emphasize some of the things, and then because Einstein.
Hello? This is Emery's work, is it?
Yeah, Emery Taylor. Yeah.
Okay.
Emery Taylor. The other one is the gauge gravity. This gauge, Coulomb gauge, can be a gauge gravity, and that I think Sang will be able to connect to vacuum friction. This one. That's I'm hoping. Once I write it, I think I can always clarify. If it makes sense to them, they can write 2 pages of derivation from their work, how it can be connected to vacuum friction. Then the gamma, the vacuum energy density, I think you should be able to connect to your work because you have done something vacuum energy, particle, and different things like your gauge, something. Again, I will write something because you presented last time. I remember it's from your presentation. You had talked about one of the things, of course, we agree that vacuum is not empty. So you had proved that there is something in the vacuum, and that converts energy density, means that the vacuum has that constant energy density in there. So I will call it your gauge, Christopher Gage or O'Neill Gage or something. So each person will have their own gauge in this one. Okay. And then finally, once we put our things together, then manual can extend to astrophysics because Hort's, John's Horde and everything, he connects to the galaxy, how the galaxies can, he talks about the sync, how the galaxies act like sync, they act like sync and all those things, and they transfer energies and things like that he was talking about. So I think it can be connected to astrophysics. And this equation, eventually, once we develop, it will be like E equal to mc squared. And you can see this is constant. So this will be like an inverse mass. It will be like inverse mass. So for quantum gravity. So when we develop completely, it becomes like a quantum gravity thing. But you can see that this is quantum, right? This is a quantum wave function. This is a relativistic gravity gauge. So you have quantum relativity, but they come together only in vacuum. That's what I was talking about. I think that was the one that was missing. I think this will set right that we cannot just extrapolate or interpolate relativity and then connect with gravity, and there's inconsistency. The same way, we cannot just magnify or what do you call micro size the quantum and say that it's like relativity. It will not happen. It can happen only, they come together only in the vacuum level, the vacuum solution. So this is like a vacuum solution of the thing that I was talking about, the physics formalism. So I think they come together here, and this is a constant according to Rosenfield, and we have to look at that. You can actually look at your thing, whether that's energy density constant. So we are going to go through that, and once it is developed, I think, so that I have gone this far only, just the initial things, but I have to start writing about that. So I want to just brainstorm. I thought John will be here, or next time we can talk when John is here, when Sang is here, but I want to ensure that I'm clarifying with you so you get an idea. You can ask questions. It may not be clear. I don't know. There may be many points which are not clear. I also not written a lot of things. So, but it's just the initial stages of our paper. Just a startup, Okay, Christopher, you can go ahead and ask questions or anything you have.
Okay, great. Yeah, very interesting. I like that. Yeah, John obviously didn't make it. Hopefully he'll be at the next one, and hopefully he'll contribute some of his research to this paper, because I think it'd be great. You know how his
probably is freezing,
of Hod's and stuff is very it's kind of unique, but there's certainly there's certainly a lot to it, and so it's nice that you're sort of using it as this kind of adds more depth to your work, and and to science in general, and it's nice that people are using each other's theories and putting them together in ways that make sense. I think it's really interesting. It's very exciting, and it's very quite fresh thinking as well, Rajan, which is
because we all have little pieces of puzzle, and we put them together. I think we can make the whole thing, the puzzle into a proper theory,
Yeah, it makes everything much more unique and more depth to all the research. So that's really good.
Yeah.
I actually really like your equation here, the way you have the psi, the wave function, and then you have the tensors, correct?
Yeah. So this is the quantum, wave function. This is our gauge, the relative. I call the gauge. So actually, the gravity. One of the reasons why the gravity is, it's actually everything has to be gauged. So it's a gauge gravity. It's not true gravity. We have to convert it later on, but it's gauge gravity. So everything is gauge, like vacuum, gauge time, and then you have wave function. See, wave function requires everything else to be gauged. That's one point we'll make it eventually, One of the things is that if you want to convert a wave function to a relativistic value, the wave function is a gauge thing. The Schrodinger thing, or actually is a gauge. So everything has to be gauged, like time has to be gauged, the gravity has to be gauged, and even the cosmological constant or the energy density. She shows in your video. So I think she shows a derivation. Let me pull up her video. I think I have her video. So let me, should I pull up that video she has where she shows that?
Go ahead.
Okay. This will be our paper before we start a theoretical. You remember 1000 volume thing?
Yeah.
We talked about, after one of these, and then after our paper with the computer simulation and the prime factorization, the magic square thing, after that we can start the theoretical the 1,000 volume thing.
But don't you think though that these papers would be part of that anyway?
Yeah, they'll be. Oh. I mean, the thing is that these papers will form the setting or the primary, way to start that, and then we'll have enough material to put them together. In that one, everything will be assembled together. These are like components, and then we assemble all of them together in that paper, in the volumes, and make the whole thing. It's probably a new paradigm we are talking about, the whole new normal science. The whole science we are developing. How all these fit together to explain the whole thing, the overall picture of the quantum and the relativity and the classical and all string theory, everything coming together,
Yeah.
So we have sufficient theoretical, and then Emmanuel comes next year, and so you will have superluminous. His theory is experimental work also will be there. He wants to work on the multi-phase systems, that we will have some papers on that. And then I was thinking, about our Hawaii and this thing. I'll give about 5 minutes, and then I'll get back to our paper written. And the idea I had recently, I thought about a brainstorm, is that we can brainstorm that a Hawaii meeting. Let's say we are able to do next year, end of next year, the Hawaii conference meeting, right?
Yeah.
After that, if we have the connection, this is the following way I thought about. It's the most mind-boggling thing. From the Hawaii, we use Bozo's blue origin, the satellite, and we all go up as a space with spacesuit and everything. Okay. Mm-hmm. And then we'll come back as aliens. I mean, we'll be in our spacesuit. Nobody will know who we are. We come back and then land in North Pole. And there we'll have the Elon Musk space platform on the space platform. And that will be like a huge ship, a dredger. We call it, I like this science fiction called Ice Station Zebra. You heard about that? Ice Station Zebra?
Yeah, I love
this is Alistair MacLean or somebody like that. I got really interested in that when I was in college. I was so, I think it's a beautiful, cool idea. So,
yeah, actually, can I interrupt you there for a second? In your paper, the one you just wrote, the one with the 6 authors.
My internet.
Yeah, the one with the 6 authors. Yes. Some of the notes that you'd written underneath. I noticed, was it Ice Station Zebra or something?
I may have written it just for me to remember a bit about it.
I was gonna ask you about it, if you were referring to Ice Station Zebra, because it was coded, but I could still work it out.
Yeah. I sometimes write this note for me to remember.
I also noticed you had like a really long function, like a sentence which was a function.
Yeah. So it's called, that's an interesting thing we'll talk about later, called metrics protocol. And I will show you. You can probably use in your IT. I developed an IT. I don't know, I can show here, maybe, I don't know whether it will be clear, but I can send this paper. But I worked on the IT area because IT is very closely related to physics, So I cannot separate the two. I had this idea about how to, I don't know, you can see this one or not clearly, but
no,
like audio phase.
Yeah.
Can you see this? Audio phase, this is audio, this is image, this is like video, and this is the text communication area. And you have the clock here. Okay. So all this I derived. I derived something called metrics protocol, it's abstract thing. Everything is derived. You'll be surprised. I have so many, but this is the output of this. So then I come up with, you are more familiar with, you will know more about this. I finally made into a matrix. called, I said matrix graphing. So this is a static screen. So what I showed you is a static screen. This is a static screen. And I can make it dynamic by using a plotter. So I use a reference axis, information on this axis, and timeline on this axis. So the timeline keeps moving, right? So the whole thing keeps moving, the whole frame. So I can timestamp it. At this point, we have certain audio, we have certain video, we have certain image, like the paper I'm showing. It could be the image, and this could be we are blogging or or chatting or something. So continuously it's moving. So it's time stamping. It's like a history. It is recording the whole thing, as it moves. So I think it'll tie in with our physics. Once we finish our physics, this is automatically say, how everything automatically flows into this, and that our real world, and also I have two 2x8 matrix here. Finally, the matrix protocol is such a thing. Even in my sleep, when I wake up, it comes in my mind, and I remember it through that. I get information. I was telling earlier, from somewhere I'm getting this information. I know from aliens. I don't know where from, but I get this communication, and it is a very powerful intelligence type of thing. So then I convert this to something called nested loop, like eight. They use in Lisp. You may have come up earlier artificial intelligence, Lisp programming. It's called Lisp programming. So I learned. I attended a couple of things. Just I was attendee. I didn't take the course, but I attended, and it was one of my friends, and I understood. I understood some more concepts about it, my own concepts regarding that. So I think the nested loop is a fundamental concept. It's a nice concept. It's like each one is like a bit, and then 8. Then later on, I said that makes sense because I attended another course with the EDX, called Harvard Computer Science Course 101. And he talks about bits and bytes nicely. This guy was talking about David Mullen, I think. So 1 bit and 8 bits make 1 byte. I'm talking a computer scientist, but that's why I understood it. You know a lot more. I mean, you probably can teach me on that. But so 1 byte. So this will make sense, and then you can poke it like a Visual Basic or Basic or Visual Basic. You can put a coordinate for this one. Like this one will be 1 coordinate, and probably you can use Excel or something to start with, or you may have better programming now with machine language. But so you can access this. It will become audio, like audio pin or audio bit, whatever you can call it. And then with quantum computer, you can use it as a audio quantum bit, maybe qubit. And then this one becomes here. It's the 4, 2 in terms of the coordinate. It becomes 4 and 2. It corresponds with the matrix. So I'm trying to correspond the matrix to this ordered pair. The matrix, like rows and columns, you say 1, 2, I think row and column, right? And then connect with in the plot, the ordered pair, X and Y coordinate, trying to see. I think there's a connection, I'm trying to bring out the connection. There's a connection. And if we connect that, we can see the whole world is like a matrix, matrix of points. You can connect everything as a matrix, you can say, and you can plot it. And it moves with time. It keeps moving with the time. All this is happening. The audio thing is happening. The video thing is happening. The image is happening. In the text communication is happening. So then this becomes the video port or video bit, qubit, whatever you can call it. So then I can arrange it, and I can put input into them, and I can output. So I think there's a direct connection between the physics and the IT automatically flows into my feeling. So we can integrate that, and you as expert, you are the, and then finally I say, here I say code. Everything is Again, I just derive it. I don't force it. It automatically comes out in my mind. Okay, it has to be a code. It tells me. So this is a code, but this code is 1 at 1, and this code is at 2, 4, and they can be different. So this code refers to audio. This code refers to video. And then eventually that will all make sense with your IT. I'm deriving it and see whether it makes sense with your IT. Probably it does, but it may need some more manipulation. So these are like switches, and I derived that they had to be like switches. So it has to be, and then I derived some matrix for that. Another one where I show that where do I show? Yeah, it's a little bit confusing, but let me see. Oops. Okay. Anyway, that somewhere. Let me write it on a piece of paper so that will make sense. So essentially what I'm saying is I can like this code, let's say it's 1, this code is is 4, 2. So this corresponds to, for example, this may correspond to
So weren't you saying about the ordered pairs? Rajan, it took ordered pairs, yeah? And
yeah, ordered pairs.
Coordinate. So, wait a second. Yeah. I'm asking you a question. You were saying that you were linking ordered pairs and then the coordinates. But I mean, surely coordinates are ordered pairs.
Yeah, no, coordinates with the matrix, rows and columns of the matrix.
I know, but you seem to be suggesting you were linking like ordered pairs with the matrix, with the rows and the columns, and I was like, but sir, that is what a matrix is. They're all properties of the matrix, are they not?
No, but the rows and columns you can convert into, when you convert into ordered pairs, do they correspond automatically, or do you have to do transform?
Well, no, you'd have to explain what you mean there, because I would have thought automatically, yes, they correspond, but so maybe, and I would have thought that was obvious. So you must be thinking about something else that I'm not thinking about.
Suppose I am saying this is 1, 1, 2, 4, 2, right? In terms of x coordinate is 4 here, right? And this is 2 here.
Yeah.
So 4, actually it should be, sorry, it should be 1. Yeah, 4, 2 according to the thing.
Okay.
According to the matrix, you count the row first, right? You do the row first. When you say matrix, suppose you're explaining as a matrix.
Yeah.
You put a row, like I say 1 by 1 matrix, right?
Yeah.
Like a 1 by 2 matrix. 1 by 2 matrix will be, or 2 by 2 matrix, or 2 by 4 matrix will be 2 rows, 4 columns, or I'm trying to think, trying to remember that. I do that, these things, but I have to refer to that. Always I know. I have to refer to that. I mean, when I do it, I check the thing, and then when I actually do the calculation.
Okay.
Modeling.
Suppose you're right. Suppose it is X, Y, which it is, but it could be different for a different setup. Like someone else could just So
I'm trying to.
So what?
So I'm trying to integrate them together to see
They
that
are
they
integrated. They are inseparable.
Yeah.
Like the index of a matrix is the matrix.
Yeah, but I'm saying that connect with the plotting, the XY plot, XY graph. If I put the matrix on a graph,
yeah,
and I connect the row and matrix to the XY coordinate.
Yeah.
So if I designate particular point like a bit, does it automatically give the matrix? I give a matrix for that. Is it same as giving ordered pairs X and Y? I'm not sure.
Pretty much. Yeah.
Pretty much.
I mean, unless you're talking about something else, like.
So I can write m of x comma y matrix m of x comma y is the same as the plot p of x comma y, the plot x comma y, the point x comma y.
You're talking way too abstractly. Are you talking about points on a screen and switches on a board, or are you talking about what?
I'm talking about if I embed a matrix, like you have
in what?
You are trying to make a breadboard, for example. You are making a breadboard. I mean, I don't know too much about that, like a breadboard.
Like this.
Yeah, exactly. Yeah, we are putting on a XY coordinate, the breadboard.
Yes, the switches, that kind of thing.
Yeah.
Cool.
And then you can move this breadboard around. They become dynamic screen.
Let's see.
They move around. They move like the axis, and the axis moves along with them.
No.
Or with reference to the axis, they can move. Like timeline.
Interesting. So what you're saying is the hardware of the computer is also the visuals.
Yes.
And something.
So it's like a moving. Yeah, it's like a moving computer, moving hardware, moving display.
Why is it moving? Where is it going?
So with the time. So I'm saying that it starts with timeline, right? Yeah. I said like we started at 1 o'clock, right? And I will say the breadboard was here, which contains all the audio, video, image, and all our things we are talking about, right? It was here, but now it has moved here. So so I'm showing that movement, and I think it's a lot of fundamental physics in that.
Okay, but let's say let's say your computer screen that you're watching me on is the breadboard, and we started at 1 o'clock your time, and it's now a couple of hours later, and the screen has moved, and the screen is now where it hasn't moved off your table.
No. But for us, we are still static screen. You see that we are using static screen, but we put on a timeline screen. Then if I show it that it is on this time, at this time, we run it. We run, when you make your video, we are running it, but we are not running it on a dynamic XY coordinate. You see that? We are not running on a dynamic, like the X coordinate is your timeline. So you're moving along the timeline and you're showing the video, how the breadboard is moving.
Well, I mean, I could.
It's like an animation or movie, I think.
it's a scrolling thing. It's scrolling across the screen.
It becomes like a virtual reality or augmented reality, probably. I don't know.
Okay, well, I'm not so sure about that because I'm just not fully tracking what you're saying. But
okay,
it's about
you can think about that. I mean, I may not be making all sense, but that's what I thought about. I think it's possible, but you may know more. You will know more. You can tell me next time.
It's just your idea could be sound, but the way you're explaining it, it's just not going in.
Yeah, I don't know that much. Maybe you have to translate it.
Oh, okay.
And also,
another thing, also, Blue Origin and going up to the North Pole, and then landing, meeting Elon Musk, and then Ice Station Zebra.
Yeah. Good point. Thank you. So let me finish that. So we landed there, right? We are all in our suit. But what happens is that ice station Cipra becomes like a dredger. It goes under like 1,000 leagues under the sea. It goes under and comes back in Siberia where Alexei is there. How mind bending is that, right? And they will come back up, and then Alexei and his torsionists, we are meeting them there, and they come there, but we are not revealed our identity yet. We are still alien, like aliens. And then Emmanuel's boss, I met them in Greece, and his boss he's a director of the institute. He's advisor, you know. So he started revealing himself. He's Antony Katas. Antony Dicus, okay? In our first paper, in our magneton paper, he's there. And Antony Dakis, I think. Antony Dakis. Emmanuel Antony Dakis. So he reveals himself and he starts talking. Then he introduces Emmanuel, right? And then Emmanuel reveals our identity because he only knows each one of us. And then the World University forms then. Like a flower, it blooms and it forms. The World University established that. Then what happens? What happens after that? It moves on to South America next year.
Nice.
The probably Machu Picchu or Peru, where Manuel is there. Manuel's Venezuela, and then it goes from there to Antarctica. And from Antarctica, then we are studying global warming and everything there. From Antarctica, it comes to your country, Ireland.
Yes.
And it could be next year. And from Ireland, it goes to Norway. Go back to the North Pole. So something like that, you know, that's kind of a idea, brainstorming idea.
I understand.
But,
I know starting off with Jeff Bezos and Blue Origin is probably the most realistic plan, but yeah, you're far worse than me. Eh? I thought I was bad.